Chapter 1.6, Transformations of Functions. So in this chapter, we will talk about vertical and horizontal shifts, reflections, vertical stretching and shrinking, horizontal stretching and shrinking, and how to graph functions involving a sequence of transformations. So transformations are all about moving our functions around. Basically, we've seen these common functions. Yes, they're supposed to be covered in this chapter, but I introduced them a little bit earlier so that we would be more familiar with them from the beginning. So those common functions that we talked about before, we are now going to be manipulating them in order to learn how to graph more complex functions. So, to begin, vertical and horizontal shifts. So given a function f of x, a new function g of x equal to f of x plus k, where k is some constant, is called a vertical shift of the function by k. So our output values, our y values, change by k units because we would have had whatever came out of f of x, but then we add k to it. So in our picture, we have, for example, f of 1 equals 1, but then f of 1 plus 1 would be 1 plus 1 is 2. So we actually end up, no matter what, if k is positive, we're shifting up by k, and if it's negative, we shift down. So, in this case, we shift the entire function f of x up by 1. Nothing else changes, we just are adding 1 to our output, so all of those y values have to shift upwards, so they are 1 more than they would have been, but the shape stays the same. On the sort of opposite end that we can do here is a horizontal shift. A horizontal shift occurs when we place that plus or minus number inside of our function. So instead of manipulating our output, we're actually manipulating our input. So given a function f of x, a new function g of x, which is equal to f of x minus h, notice that this is all within f. We are plugging x minus h inside of f. So we're replacing x with x minus h instead of just tacking this k on at the end the way we did for the vertical shift. That gives us a horizontal shift. So our output values haven't changed, they just occur h units later than in f. So in other words, all of our y values stay the same. So look in the picture. All the y values are exactly the same. We haven't changed our range, we haven't changed our shape or anything like that, but they've moved over so that a different x value would have to be plugged in order to obtain them. So this causes, if h is positive, a shift to the right, and if h is negative, a shift to the left. And so you'll notice a theme with these vertical versus horizontal transformations that we're running into, is that horizontal ones sort of do the opposite of what you want. So essentially, the default for a horizontal shift is minus h, because if I have, for example here, f of x plus 1, I'm actually subtracting 1 from all of my x values, so everything is shifting to the left one. Generally, you see plus 1, you might think, oh, go to the right, because that's the positive side. Horizontal shifts just do the opposite of what you want them to be. So if it had been f of x minus 3, then we would shift to the left by 3. We would shift to the right by 3. We would head this way. Even though it says minus 3, you do the opposite of what you would sort of expect. And that's kind of how horizontal stuff works, is because we're affecting the inside, the input, so our output has to shift earlier in a way, so things get kind of shifted weird. So just remember, horizontal stuff on the when we're plugging stuff in to f of x, it's gonna do the opposite of what you want. Alright, so let's look at what this looks like in a table. So if we have x and f of x, and then I've defined for a vertical shift, g of x equals f of x minus 3. So vertical shift just means I just subtract 3 from all of those output values. So I'm going to take 1 and subtract 3. So I get negative 2. Do this for everything. Just keep subtracting 3 from every output. So I'm getting g of 2 would be, remember, g of 2 equals f of 2 minus 3. But we know f of 2 is 1, so 1 minus 3, which equals negative 2. So that's how that works. But for a horizontal shift, on the other hand, it's a little bit trickier. Horizontal stuff is always a little bit trickier. We want to say, well, we know how x and f of x interact. So what if I say x minus 3 is 2, 4, 6, 8? Because that's what I was given. So I know that f of x minus 3 would be this. Okay, so that's strange, though. If I'm saying x minus 3 is 2, then f of x minus 3 has to be 1, because that's what I was told over here. If x minus 3 is 4, then f of x minus 3 is 3, because that's what I was told right here, and so on. Okay. But how does that really help me? Well, what I want to think about is, then what is x? So essentially, if x minus 3 is 2, then x would have had to be 5, right? Because 5 minus 3 is 2. And then we can do that for all the other ones. 7 minus 3 is 4. 9 minus 3 is 6. 11 minus 3 is 8. So if x minus 3 is 8, then x would have had to be 11. So in other words, g of 11 should be the same as f of 8. Now that's a little weird, right? But that's essentially what we're saying, is that all of those output values haven't changed. What has changed is when they occur. So if for a vertical shift, the output values are actually changing. The output values have shifted it up or down by whatever is added or subtracted on the outside. But for a horizontal shift, our outputs, our end values, our y values, don't change. They just change where they're occurring. So in this case, g of 7 is the same thing as saying f of 7 minus 3, which is to say f of 4. And we know f of 4 is 3. So g of 7 is 3. So all these same numbers that occurred in f of x occur in g of x. They just occur at a different value of x. All right. So if I wanted to combine these shifts graphically, how could I do it? So we're going to start by remembering our common functions. I'm going to graph the absolute value of x, which looks like this, okay? And then I want to start by looking at horizontal or vertical. I get to decide where I start with horizontal or vertical. I pretty much always start with the horizontal stuff. I work from the inside out. That's just my choice. You don't necessarily have to do that. I will talk about the order you have to do these transformations in a little bit later, but for right now, I'm going to start with the horizontal shift. So, horizontal shift, we have this plus 1 inside of our f. So, h equals negative 1 means we're shifting to the left by 1. Because again, it's x plus 1, but really we have to think of it as x minus h, so h is negative 1, that's what's going on here, but really, if there's a plus, then we don't go to the positive side, we go towards the negative side, because horizontal stuff just works backwards. So, we shift to the left by 1, so our new function's going to look like this. So this is f of x plus 1, but we're not done yet, because we still have to think about that negative 3. That negative 3 is a vertical shift, and now it works the way we want it to, so negative 3 is a shift down by 3, and so our final answer is going to look like this. So we have this interim step, but our final answer has shifted to the left 1 and down 3, and so this is f of x plus 1 minus 3. So if we had done it in a different order, if I had shifted down first, then I would have had, let's try that again. I would have had here, like this, So that's down 3, and then I would have gone to the left 1, and so I would have ended up with the same exact function. So you can do it in a different order, but there are some rules to that ordering that, again, I will talk about later once we've defined the other types of transformations. So, our second type of transformation being reflections. Given a function f of x, a new function g of x equal to negative f of x is a vertical reflection of the function f of x, sometimes called a reflection about or over the x-axis. So you'll hear all of these terms. Most often it'll be an x-axis reflection or a reflection over the x-axis. Like, that's the most common way it's said, but it is technically a vertical reflection is what, to group it in with these vertical transformations versus horizontal transformations. So, a vertical reflection or a x-axis reflection takes our function and flips it over the x-axis. So we can see we have this this function, the original function f of x, and then negative f of x flips everything over. So it changes the sign of all output values. So once again, remember, stuff that's happening outside of f of x. So when we have the vertical shifts, and when we have the vertical reflection, and eventually we will learn about the third type of transformation and its vertical component, always happen outside of our function. So we are changing our output values. Our y values have entirely changed here. All of the y values are now different. They are the negative form of what they were before. If they had been negative, they would become positive, etc. So the other side of that would then be the horizontal reflection, which is when we plug that negative inside. So f of negative x is a horizontal reflection. So this is when we are affecting the inside of our function, we are affecting the input instead of the output. So all of our y values remain the same, but it just changes when they occur. So here we get what's called a y-axis reflection. That will be more often what you hear is y-axis reflection, but it is a horizontal reflection. So we can see that this original function would then just be flipped directly over the y-axis in the same way that it was flipped over the x-axis for the vertical reflection. So output values switch sides of the y-axis. So if they were on the left, they end up on the right, and vice versa. But again, those values did not change. It just changed when they occurred. So if we look at the tabular form of these types of reflections, again, I'm starting with the same x, f of x, and we're going to look at first the vertical reflection, g of x equal to negative f of x. So this is the easiest one to do. All we have to do is negate or add a negative to all of the f of x outputs. So we take 1, comes negative 1. Take 3, comes negative 3. Negative 7, negative 11, and that's it. So g of 2 is the same as saying negative f of 2, which is negative 1, which is negative 1. But, again, with the horizontal reflection, it's a little trickier than that. So, for the horizontal reflection, we have to think about what we know versus what we need to learn. We are changing our input instead of changing our output. So if we say what we know is if negative x were 2, 4, 6, 8, then f of negative x are 1, 3, 7, 11. That's what we know from over here. Then what would x have to have been? Well, first, if negative x is 2, then positive x is negative 2. If negative x is 4, positive x is negative 4, which is a little confusing to say, but just solve the equation and it makes a little bit more sense. So we get this, and then that tells us that, well, we've already sort of figured out what's going on here. G of negative 4 is equal to f of negative 4, which is to say f of 4. And we know that f of 4 is 3. so it better be 3 right here. And the same goes for all of the other numbers as well. So again, our outputs, our y values never change. They're the same as they were for f. They're the same as they were for the original f. But the input that got us there has changed. So g of negative 2 instead of f of 2 is what is happening to get us those output values. Now, what about if we want to combine reflections with shifts? So here I have a graph that you don't need to know how to graph yet. This is something we will learn later. But I'm showing you the graph just to sort of give you a primer for something we'll learn in chapter 3. So this is the graph of 2 to the power of t. But it's important that even if you don't know what type of function this is or how to work with this type of function, if you're given the graph, then you should be able to recognize what's happening to it, because you just have to look at where x or t or whatever the variable is. So in this case, we have I'm so sorry, this should say k of t, the variable is t, so make sure in your notes you change that. K of t equals negative 2 to the negative t plus 1. So what we have changed from that base function of 2 to the power of t is we've put a negative in front of the t and a negative in front of the 2, and then we've added 1 outside. So where the t was, if we're like up in that little box up here, what changed was that a negative was applied to it. So that means we have a horizontal reflection, that 2 to the negative t. So we can apply that horizontal reflection. So all we really need, we don't even need to know anything about this function. All we need to know is what the graph was and what has happened to it. So here, 2 to the negative t would then be a horizontal reflection over the y-axis. Okay, then we know that there is a negative out front, so negative 2 to the negative t then becomes a vertical reflection over the x-axis next. So we get reflection over the x-axis, and then finally we have another step where we now have this vertical shift. So we shift everything up by 1 because that's what the vertical shift does. And so now we have a final function, and if we plugged into it, we would see that this works this way and all of that. Make sure that even if you don't know much about the function, you're paying attention to a few points that you're given or something like that, because you will be given just straight up graphs where you don't know what the function was, you're just told to do these transformations to them. So not knowing about the exponential 2 to the t or what that graph looks like, as long as you're given it, it doesn't matter if you know what negative 2 to the negative t plus 1 should look like. As long as you're given a starting graph, you can do all of these transformations. So that's the point of this problem. All right, so let's do a quick review of even and odd functions. We saw even and odd functions back in chapter 1.3, but I talked about some symmetry that related to those even and odd functions, and now let's think about how that can relate to our horizontal and vertical reflections that we just talked about. So a function is even if f of x equals f of negative x. Well, f of negative x is a horizontal flip. So in other words, even functions remain the same after a horizontal reflection, which is y-axis symmetry. So in other words, if I do a horizontal flip and nothing changes, then I have an even function, because it ends up equaling the original equation, and doing that y-axis flip ends up giving me the original equation, or giving me the original graph. Whereas for an odd function, that rotational symmetry, by definition, an odd function is f of x equal to negative f of negative x. So we applied a horizontal shift, and then we apply a vertical shift. So if we do both of those things and it looks like the original graph, Well, let's check. If I'm looking at this graph of x cubed over here, then first I do my my horizontal flip over the y-axis, right? So I do that. Then I do my vertical flip over the y-axis, and if it's drawn precisely, you'll see that it is exactly the same as the original graph. So when that happens, we have an odd function. So even and odd functions are all about doing those transformations and seeing how their symmetry works out. So rotational symmetry is just doing is just doing a horizontal and vertical flip and getting back the original graph. That's what rotational symmetry is, whereas y-axis symmetry just means doing a horizontal reflection and getting back the original graph. Alright, so our last type of transformation that we're going to cover is stretches and compressions. These are usually the most tricky of the types of transformations we talk about. So first, a vertical stretch or vertical compression occurs when we multiply f of x by some number. Specifically, if the number we're multiplying by is greater than 1, if its absolute value is greater than 1, the graph will be stretched. But if it is less than 1, it will be compressed. So, if it is negative, if the number is negative, if a is negative, well, we're doing a stretch or a compression, but we're also doing a reflection. So that's why we talk about this as just the absolute value of a, is because just it being negative means there's a reflection involved as well, because we've taken a reflection and we've taken this stretch. So if it were -2, we would do a reflection and then we would do a stretch, or a stretch and then a reflection. It doesn't actually matter which order you do it in. All right. So again, our vertical stuff works kind of the way you would think that big number, big stretch, small number, kind of you're halving it, or you are thirding it, or whatever. So that's essentially what's happening. If we look at this graph, yes, 2 times f of x, we are getting our output 2 times greater. We have pulled away from the y-axis. That's what vertical stretch is all about, is from the x-axis. Vertical stretch is all about pulling away from the x-axis. So we take our whole graph, pick it up, and pull it upward. Every piece of it just gets pulled upward by 2 or 7 or whatever number you're multiplying by. Or it gets pushed downward. That's what a compression is we're just pushing everything towards the x-axis. But for a horizontal stretch, it's of course going to be slightly different and not necessarily what we want it to be. So if we have b times x being plugged into f of x to get our new function, well then that is a horizontal stretch or horizontal compression. But the difference is that if b is larger than 1, we compress. And if b is less than 1, then we stretch. And again, if it is less than 0, like not absolute value, but if b is less than 0, we also get a reflection in there along with it. So here, if we look at this function, which was originally x squared, and we have 2x squared, we have compressed it in towards the y-axis. And then 0.5x squared, we have pulled it away from the y-axis. And so again, the output values didn't change, but it does change where they occur. But it does the opposite of what you would necessarily expect. So we are getting sort of flatter in a way by pulling away from the y-axis, but it does feel like we are enlarging it. So it's just think horizontal stuff, the opposite of what you expect. So 1 over b is what we are stretched or compressed by, no matter what. Okay. So let's look at this in its tabular form as well. So again, same function as before, but now we have g of x equals 1/2 f of x. and g of x equals f of 1/2 x. So if we start with the vertical compression, again, pretty simply, we just multiply all of our outputs by 1/2. So 1 becomes 1/2, 3 becomes 3/2, and so on. So here we get g of 6 equals 1/2 times f of 6, which is 1/2 times 7, or in other words, 7/2. But for the horizontal stretch, again, we're going to start off by defining 1/2 x to be the stuff that we know information about, so that f of 1/2 x is, again, the things we know information about. And we look back and figure out, okay, so what was x? Well, 1/2 x equals 2, so x would have to then have been 4, right? Because 1/2 times 4 equals 2. 1/2 times 8 equals 4. 1/2 times 12 equals 6, and so on. So 1/2 x, 2, 4, 6, 8. So x, 4, 8, 12, 16. And again, just as you've probably come to expect, that means that our g of x's are just going to be a repeat of f of 1/2 x as they're supposed to be. So g of, let's say, 8 equals f of 1/2 times 8, or in other words, f of 4, which we know to be 3, and so on. So all of those are going to repeat. So what happened, once again, same as before, our horizontal stretch does not change our output values, but our input values, our x values, are what are affected. Now let's put all of this together. So it's important to know the sequence of transformations. As I said back at the beginning, you're allowed to do a little bit of change in here, but in general, there are some rules you have to follow when doing a sequence of multiple transformations. There are certain transformations that have to come first or second, etc. So you're always allowed to pick whether you want to start with vertical stuff or horizontal stuff, but you should do all of them at a time. So if we're starting with vertical stuff, with the vertical transformations, a f of x plus k, we do our stretch and reflection, doesn't matter which order, just together, vertically by a, and then we shift vertically by k. So notice the shift comes second, always. So stretch and reflection can, or a third, I guess, if you include the stretch or reflection, whichever is occurring, those happen at the same time, so it doesn't really matter which one of those happens first, as long as the shift happens last. Next, with horizontal transformations, we have f of bx minus bh. Notice that I've said this a little bit weird, and that's for a very specific reason. It's because whenever you're given a horizontal transformation, whatever is multiplied by x, you have to factor out of whatever is being added or subtracted from x. So if there is a horizontal shift along with a stretch or a reflection, you have to factor it out every single time or your answer will be wrong. Because of course, horizontal transformations always have to be a little bit difficult. So we factor out our whatever was multiplied by x, in this case b, and then we stretch or reflect horizontally by 1 over b. If there's a reflection, that again happens at the same time as well. And then we do our shift at the end by, in this case, h. So make sure you are factoring out b. If you do not, you will get a different answer. You can test this to see why. It's very good to see visually that this does cause a difference in your answer. If you don't factor it out, you will end up shifting in the wrong direction or by the wrong amount, etc. So, horizontal and vertical transformations are independent, though. It doesn't matter which is performed first as long as you're doing them in this order. So, stretches and reflections and followed by shifts. That's the order you have to do it in. Doesn't matter whether it's vertical or horizontal, just make sure the shifts come last. Alright, so let's apply all of our knowledge so far. So here I have a function, k of x equals negative f of 1/2 x plus 1 minus 3. So it's got basically everything going on. So, once again, remember, I like to start with horizontal transformations. That's just my personal preference, so that's where I'm going to start. But when I start with horizontal transformations, it means I have to start by factoring out this number. So I'm going to rewrite this inside of f factored so that it is 1/2 x plus 2. So that's what it looks like when I factor out 1/2. Alright, now I will start by doing my horizontal transformation of a horizontal stretch by 2. So remember, again, it is 1/2, and so it's 1 over b, so 1 over 1/2, which is 2. So this is 1 over 1/2, so that's 2. So I'm doing a horizontal stretch by a factor of 2. So what that means is I'm going to take this graph and I'm going to pull it away from the y-axis by 2. So I'm going to multiply everything by 2, pulling it away from the y-axis. So it's going to look like this. So it's twice as wide, essentially. Alright, so that's f of 1/2 x. Then, next, I'm going to deal with my horizontal shift, which, because it is plus 2, I'm shifting to the left, because again, plus 2 on the inside for a horizontal shift does the opposite of what you'd expect, so it's heading towards the negative side of the coordinate system. So we are going to the left 2. So the whole thing gets shifted over to the left by 2. Alright? So, if I had done this in the wrong order, it wouldn't have shifted to the left by 2. It would have shifted the wrong amount. And so we would have a completely different function. Again, I'm not going to show you the wrong answer here, but try doing it in that way. Show yourself that it is different if you do this in the wrong order, so that you can remember that it has to be done in this order. Alright, now I'm going to move on to the vertical transformation. So first vertical transformation that we can highlight is the fact that there is a negative outside of my f, right? It goes negative f of 1/2 x plus 2 minus 3. So that negative means I'm going to be reflecting over the x-axis. So I do my reflection over x. Then my last step is the shift down by 3. Notice that, again, for horizontal stuff, I had to factor out my 1/2 and all of that. I don't have to do that for vertical. Vertical is just nice and works the way you want it to every time. So I can just shift down by 3. I didn't have to factor out that negative or anything weird like that. So I shift down by 3, and that's my final answer. So here we have our final half circle sort of situation. It's not really a circle anymore, but our final sort of curve situation. So again, I really encourage you to go through and test this yourself. Try and draw some graph. Doesn't matter what the graph is. Start from some graph, and then apply these transformations to it to check yourself and make sure you know how to do these transformations. So here, again, we have some practice with each of their graphs, so you can go through and test yourself on all of them.